Okay, we're going to get started with sampling distributions, specifically with regards to proportions. So what I'm going to do is the lesson we did in class, I'm just going to try and go through it relatively quickly. So, share. Okay, so we're going to look at this about what proportion of orange, what proportion of Reese's Pieces are orange. So suppose a large bag of Reese's Pieces has 1,000 pieces. The manufacturer says that exactly 40% of the candies are orange. If we selected a sample of 50 pieces, how many would be orange? Let X equal the number of orange. So this is a little bit of a review. If you think about this one, this is a binomial setting. And the reason it's a binomial setting, if we remember from before break, B stands for binary. Is there a success? Is there a failure? So what we're going to say is that orange is a success. So orange is a success. And a failure is not orange. The next one is independent. And what we need to think about with independent is a couple things. One thing is, in this case, we can assume that like the color of one has no influence on another, but here's something new we're going to talk about. It's something I mentioned last class. It's called the 10% rule. The 10% rule is, since we're not putting the candy back in the bag, what we need to do is we need to make sure that our sample is not more than 10% of the population. So in this case, the population of the bag is 1,000. I'm taking a sample of size 50. So what I'm going to do is do a quick check. What I'm going to say is, well, what is 10% of 1,000, or what's easier to do? What's 10 times 50? 10 times 50 is 500. 500 is less than 1,000. 500 is less than 1,000. So we can assume independence. And this is how we're going to handle it. We're going to do a 10, it's called a 10N check. We're going to take 10 times the sample size, make sure it's less than the population. That's how we can prove independence when we're not replacing something in a bag. N is our fixed number of trials. So we have a fixed number of trials. And in this case, our N is equal to 50. And then S is the success probability has to stay the same each time. And in this case, the success probability is 0.4. So we have a binomial setting. So now what I'm going to do is I'm going to use a simulator online to do it. So we're going to try and do this in class. We're going to use calculator, I think, to handle it. So, but what we're going to do right here is the probability of me being orange is 40%. I'm taking 50 candies. And what's going to happen is I'm going to show you the animation, but I'll do it without animation next. So what will happen is this. I'll draw a sample. What it's doing is it's pouring the candies out. It's counting them up. Orange, yellow, and brown. When we get to 50, what that says is I got 19 the first time. So what ends up happening is I got 19. So now what I'm going to do, I'm going to do it 4 more times. Turn off the animation because it goes a little bit quicker. So I ended up, if we look down here at the bottom, I ended up getting a 17. I ended up getting a 21. I ended up getting a 23, and I ended up getting a 24. So now what's going to happen is we're going to put those, so again, what ended up happening, let me go back and show you. I ended up with the following 5 samples: 19 orange, 17 orange, 21 orange, 23 orange, 24 orange. So now what we would do is we would do this on the board. What I'm going to show you is, instead of doing that, I am going to do a quick simulation here. And what I'm going to do is I'm going to do it 995 more times. Okay, so there. If we look down here, this right here is my distribution. If you kind of look at my distribution here, this is what I would expect. And if you look at this, when we go to kind of sketch this roughly, it's centered at about 20. It's about 19 or 20 right there. I'd say that's 19. I'd say center at 19. It is roughly symmetric. It is roughly symmetric. And if we kind of did a quick look, we can see that we went everywhere from 29 to, it looks like we had one down here at 10. So we had a range of 20. So there's our dot plot. Okay, we're going to have it on the board. This is just a simulation of it. And we'll go back and take a look again. And so this one will be that picture we had that I just showed you. What does each dot represent? Each dot represents a sample. of 50 Reese's Pieces. Okay, so now, what does the mean and the standard deviation? This is from your formula sheet. The mean of a binomial is equal to n times p. So 50 times 0.4, we're talking 20 orange pieces. We would expect 20 orange. Standard deviation from our formula sheet, standard deviation of a binomial, is n p 1 minus p. So in this case, it is the square root of 50 times 0.4 times 0.6. And the answer to that is 3.46 orange pieces. So what we would expect is this sample would have on average 20 oranges with a standard deviation of about 3.5 oranges. And again, let's go back and take a look at the picture again. Pretty close. I mean, in this case, that's 18, 19, 20. We're saying 20. Our sample is close to it. And in terms of the shape right here, what we can take a look at is we can determine the shape, because again, you would say roughly symmetric, but here's a new thing we're allowed to say. A new thing we're allowed to say is the following. We can now do what's called the rule of 10. If we have 10 successes, if we can anticipate 10 successes and 10 failures, we can make a conclusion. So what I mean in this case, let's do 50 times my success probability of 0.4 is 20. If I did 50 times 0.6, my success probability is 30. Both of those numbers are greater than or equal to 10. Since that is true, I can describe this shape as approximately normal. It's now a rule I'm allowed to. I can move beyond roughly symmetric. I can now say something is approximately normal because I have 10 or more successes and I have 10 or more failures. So what I really have at the end of this is I can say that this distribution that I'm dealing with is going to be normal with a mean of 20 and a standard deviation of 3.46. This would describe n for normal. That's going to be what I would anticipate my mean to be, or my x bar to be. And that would be my standard deviation. So this is kind of a new thing we're going to look at. Instead of describing shapes as roughly symmetric, we're going to use this rule of 10 to determine if something is approximately normal or not. Again, the reason for that is if something is approximately normal, we can use some of our rules and some formulas that have already been predetermined for us to calculate some probabilities. So I'm going to pause it on this one, and then I'm going to do the second one to talk about the backside of this.